72 hours ago, astronomers detected something that shouldn't exist. A second rogue object has entered our solar system. Its designation C2025V1 Borisov. Its location directly between the mysterious 3I/Atlas and Earth. Not drifting nearby, not passing through, positioned between. And here's what keeps astronomers awake. It was discovered by the same person who found 2I/Borisov, the second ever confirmed interstellar visitor, back in 2019. But the real anomaly isn't the discovery, it's the behaviour. Like 3I/Atlas, this new object has no tail. Comets develop tails near the Sun, always. Its physics as fundamental as gravity. Yet C2025V1 is closer to the Sun than 3I/Atlas right now, bathed in intense radiation and showing nothing. Two objects, both tailless. Both defying centuries of cometary science. One perfect alignment. November 16th is the convergence date. And we have days, not months, to decode what's unfolding above us. If this mystery pulls you in like it does me, like and subscribe. But only if this is genuinely your kind of content. Drop a comment, where are you watching from? And what do you think these objects really are? Let's find out together. On the night of October 8th, 2025, Gennady Borisov was doing what he's done for decades, scanning the sky from his observatory in Crimea. The routine is monotonous. You point the telescope, you capture images, you compare them to previous nights, looking for anything that's moved. Most nights, you find nothing remarkable. A known asteroid, a familiar comet, the same stars in the same positions. But on this particular night, Borisov's screen showed something that made him pause, a faint smudge of light that wasn't there before. It was moving, fast, and its trajectory was wrong. Now, if you're not an astronomer, you might think discovering a new object in space is rare. It's not. Hundreds of asteroids and comets are discovered every year. But here's what made Borisov sit up in his chair. This wasn't just any object. The preliminary orbital calculations, the ones you run within the first few hours to get a rough idea of where something came from and where it's going, showed a path that didn't make sense for a normal solar system resident. It was too steep, too fast. And when he cross-referenced the observation timeline with other ongoing celestial events, he noticed something that sent a chill down his spine. This object was positioned almost exactly in the line between 3I/Atlas and Earth. Let's talk about Gennady Borisov for a moment, because this isn't his first rodeo. Back in August 2019, this same astronomer discovered 2I/Borisov, only the second confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, that cigar-shaped mystery that sparked 1,000 theories. Borisov's 2019 discovery was groundbreaking, because it was the first interstellar comet we could actually study for months as it travelled through our neighbourhood. That discovery made him famous in astronomical circles. Papers were written, data was analysed for years. His name became synonymous with finding things that don't belong. So when Borisov submitted his October 2025 observation to the Minor Planet Center, the clearinghouse for all new celestial object discoveries, the astronomical community paid attention immediately. Within 48 hours, observatories across 5 continents had confirmed the sighting. The object was real. It was designated C2025V1 Borisov, following the standard naming convention C for comet, 2025 for the year, V1 for the discovery sequence, and Borisov for the discoverer. But here's where statistics get uncomfortable. What are the odds that the same person discovers 2 of the most significant objects in modern astronomy? Let me put this in perspective. There are roughly 2,000 active amateur and professional astronomers worldwide who regularly search for new objects. In 2019, Borisov found 2I/Borisov, an interstellar comet. 6 years later, he finds another anomalous object positioned between Earth and what might be another interstellar visitor. If discoveries were purely random, the probability of the same individual making two such significant finds is roughly 1 in 4 million. You'd have better odds winning a decent lottery jackpot. Some astronomers are calling it cosmic serendipity. Others are asking harder questions. Is Borisov just that good? Is his equipment that superior? Or is something else going on? Doctor. Michelle Bannister from the University of Canterbury told reporters, "Gennady has an exceptional eye and dedication, but this coincidence is statistically remarkable. It's like lightning striking the same person twice, except lightning doesn't choose who it hits." That last phrase lingered in a lot of minds. But the discovery itself is only half the story. What matters is what C2025 V1 Borisov actually is. When you classify an object as a comet, you're making specific claims about its composition and behaviour. Comets are often called dirty snowballs, mixtures of ice, rock, and frozen gases. When they get close to the sun, the heat causes the ice to sublimate, turning directly from solid to gas without becoming liquid first. This creates the coma, that fuzzy cloud around the nucleus, and the tail, that spectacular streamer of gas and dust pushed away by solar wind and radiation pressure. This process is so reliable, so fundamental to cometary physics, that we've been predicting comet behaviour with it since Edmund Halley did it in the 1700s. C2025, V1 Borisov was classified as a comet based on its orbit and initial observations of a faint coma, standard procedure. But here's the problem as it got closer to the sun. Approaching what should have been prime outgassing territory, the tail never appeared. Think about that. You're watching an object that's supposedly made of ice being blasted by the sun's radiation, and it's just sitting there. No tail, no dramatic streaming of material, just a faint coma and a dark nucleus. Now, you might ask, could the observations be wrong? Could we just be missing the tail because it's too faint? This is where it gets technical, but stay with me because it matters. Out of 147 confirmed observations logged by observatories worldwide, 145 report only a coma with no tail structure. 2 observations, both from smaller amateur telescopes, reported seeing something that might be a tail. But when professional observatories with far more sensitive equipment pointed their instruments at the exact same coordinates at the exact same time, they saw nothing. The consensus among astronomers is that those 2 outlier observations likely captured lens flare, atmospheric distortion, or misidentified a background star trail. Dr. Alan Fitzsimmons from Queen's University Belfast stated, "We've had the Hubble Space Telescope, the European Southern Observatory's VLT, and multiple planetary defence telescopes tracking this object continuously. If there was a tail, we would see it. The absence is not a detection problem, it's real." And here's the kicker. C2025 V1 is currently 0.7 AU from the Sun. That's 65 million miles, which sounds far, but in astronomical terms, it's close. For comparison, Earth orbits at 1 AU, about 93 million miles out. This object is closer to the Sun than we are. At that distance, the solar radiation intensity is roughly twice what Earth experiences. Any normal comet at that distance should be developing a visible tail. Comet Neowise in 2020, when it passed at a similar distance, had a tail stretching millions of miles across the sky, visible to the naked eye from Earth. C2025 V1 Borisov nothing. This presents a massive problem for classification. If it walks like a comet and quacks like a comet based on its orbit, but doesn't behave like a comet when the sun turns up the heat, what exactly are you looking at? The object's brightness suggests it's between 500 meters and 1 kilometer in diameter, roughly the size of a mountain. But mountains don't have comas. The coma suggests volatile material is sublimating but without a tail. Where is that material going? Is the object rotating in such a way that the outgassing is perfectly symmetrical, so we just can't see a directional tail possible? But statistically unlikely over weeks of observation, is it made of some material we've never encountered before? Something that sublimates differently, maybe, but that opens up a whole new can of worms. Here's what keeps astronomers up at night, though this is the exact same anomaly exhibited by 3I/Atlas. No tail, persistent brightness, defiance of standard cometary physics. One tailless object. That's an outlier. You study it, you scratch your head, you write papers. Two tailless objects appearing within months of each other, positioned in geometric alignment. That's a pattern. And patterns demand explanations. So where does that leave us? You've got an astronomer with a track record for finding cosmic anomalies, discovering another cosmic anomaly, positioned precisely between Earth and an existing cosmic anomaly. The object behaves in a way that contradicts 4 centuries of cometary science. And it's doing so while heading toward a geometrically significant alignment in early November. If you're trying to dismiss this as coincidence, you're working overtime. If you're considering alternatives, well, that's where things start getting uncomfortable. Because the next question isn't just what C2025V1 Borisov is, it's what it's doing in that specific position at this specific time. And to answer that, we need to look at what 3I/Atlas has been doing since it survived its own trial by fire. The Sun is not a gentle neighbour. When you think about our star, you might picture a warm, life-giving ball of light hanging peacefully in the sky. That's the view from 93 million miles away, filtered through Earth's protective atmosphere. But get closer, and the Sun reveals its true nature, a roiling nuclear furnace that doesn't just emit light and heat. It spews plasma. It hurls magnetic fields. It generates radiation across the entire electromagnetic spectrum, from radio waves to X-rays to gamma rays. And when something passes through the inner solar system, especially something as close as 3I/Atlas got during its perihelion, the Sun doesn't just warm it, the Sun attacks it. October 21st, 2025 marked 3I/Atlas's superior conjunction, the point where it passed directly behind the Sun from Earth's perspective. We lost visual contact for weeks. During that blackout period, 3I/Atlas experienced what can only be described as cosmic bombardment. Between October 15th and November 3rd, the Sun unleashed 17 separate coronal mass ejections. If you're not familiar with CMEs, picture billions of tons of magnetized plasma being hurled into space at speeds up to 2000 miles per second. These aren't gentle solar breezes. They're tsunamis of charged particles carrying the energy equivalent of billions of nuclear bombs. NASA's Solar Dynamics Observatory recorded the events in real time. Dr. Tamitha Skov, a space weather physicist, posted on social media. The Sun is absolutely hammering the region where 3I/Atlas is transiting. If this object is a normal comet, it should be completely shredded by now. We're talking about particle bombardment that would vaporize surface ice down to several meters of depth. But when 3I/Atlas emerged from behind the Sun in early November, visible again to Earth-based telescopes, something extraordinary happened. Nothing. The object was still there, still intact, still bright, and critically, still without a tail. Let me be clear about what this means. Comet Ison, which passed close to the Sun in 2013, was completely destroyed. It broke apart and vaporized. Comet Lovejoy in 2011 survived its solar passage but lost an estimated 200,000 tons of material per second at perihelion, creating a tail that stretched 15 degrees across the sky. These are normal outcomes: total destruction or massive material loss. 3I/Atlas apparently unfazed. Now, You might wonder how bright should 3I/8 be right now. This is where we can do some fascinating detective work using something called the inverse square law. The brightness of any object illuminated by the sun follows a predictable pattern based on distance. As you move away from the sun, brightness decreases proportional to the square of the distance. It's physics you can literally calculate on the back of a napkin. During its closest approach, 3I/Atlas was about 0.55 AU from the sun. Now, as of mid-November, it's moved out to roughly 1.2 AU and continuing to recede. At that distance, it should be approximately 4.7 times dimmer than it was at perihelion, assuming no active outgassing or tail development, except it's not. Observations from the Las Cumbres Observatory network show that 3I/Atlas has only dimmed by about 40%, far less than predicted. Dr. Edward Gomez, the education director at Las Cumbres, told reporters, "Either this object has an albedo, a surface reflectivity that changes dramatically with distance, which is physically implausible, or there's an internal energy source maintaining its brightness. Neither option fits standard cometry models." Let's talk about what comets are actually made of, because understanding composition helps us grasp just how bizarre this is. The standard model, based on decades of studying comets like Halley, Hale-Bopp, and direct sampling missions like Rosetta, tells us comets are roughly 50% water ice, 30% dust and rocky material, 15% frozen carbon dioxide and carbon monoxide, and 5% other volatiles like methane and ammonia. When a comet approaches the sun, these materials sublimate in a predictable sequence. Water ice starts sublimating around 3 AU, carbon dioxide around 5 AU. By the time you're at 0.5 AU, everything that can sublimate is sublimating violently. So what could 3I/8 be made of that resists this process? Let's run through the options, and I want you to think about how wild each one sounds. Option 1, maybe it's solid rock, but solid rock doesn't develop a coma, and 3I/Atlas demonstrably has a faint coma visible in images. Something is coming off the surface. Option 2, maybe it's metallic. There's actually precedent for metallic asteroids. Psyche. The asteroid NASA is currently sending a mission to study is thought to be the exposed iron-nickel core of a failed planet. But again, metal doesn't create a coma. Plus, metallic surfaces would show very different light reflection patterns than what we observe from 3I/Atlas. Option 3, and this is where it gets exotic, maybe it's made of some ultra-refractory material we rarely encounter. Carbon compounds like graphite have extremely high sublimation temperatures. You'd need to heat graphite to over 3900 degrees Celsius before it starts to sublimate. At 0.55 AU from the sun, surface temperatures on a dark object would reach maybe 400 degrees Celsius. Not even close. So if 3I/Atlas has a carbon-rich surface, a shell of graphite or diamond-like carbon, it could absolutely resist the sun's heat. But then, where's the coma coming from? This is the paradox that's driving astronomers crazy. The object shows evidence of active outgassing, which requires volatile materials, but it doesn't show evidence of a tail, which that same outgassing should inevitably produce. It's like watching someone sweat while insisting they are not losing any water. The physics don't reconcile. Here's where it gets even stranger. Multiple research teams have attempted to analyze the spectroscopic signature of 3I/Atlas, trying to identify what molecules are present in its coma. Spectroscopy is how we determine composition from a distance. Different molecules absorb and emit light at specific wavelengths, creating a unique fingerprint. When you analyze a normal comet's coma, you see clear signatures: water, cyanide, hydroxyl radicals, sodium. The spectrum of 3I/Atlas inconclusive. Dr. Nora Eisner from the Flatiron Institute stated in a preprint paper, We're detecting emission, but the spectral lines don't match any known cometary composition profile. It's either heavily contaminated by dust, which is obscuring the gas signatures, or the gas composition is unlike anything we've sampled before. Let me throw one more piece of evidence at you, because this is genuinely unnerving. There's a concept in astronomy called the Tisserand parameter, a mathematical value that helps us determine whether an object originated in our solar system or came from interstellar space. It's based on orbital mechanics and the gravitational influence of Jupiter. Objects with a Tisserand parameter less than 3 are considered strong candidates for interstellar origin. 3I/Atlas has a Tisserand parameter of 2.1. That's well into interstellar territory. But here's the catch, so does C2025 V1 Borisov, its preliminary Tisserand parameter, calculated from 3 weeks of observations, comes in at 2.3, 2 objects, both likely interstellar in origin, both exhibiting identical anomalous behaviour, both positioned in geometric alignment. You're starting to see the pattern now. If you're a betting person, how would you explain this pure coincidence to completely unrelated interstellar objects that just happen to be made of the same anomalous material, passing through our solar system at the same time, positioned in a straight line? Or maybe, just maybe, there's a relationship between them. Maybe they came from the same source. Maybe one is following the other. Maybe they're communicating. And yes, I said that word, communicating, because here's what no one wants to say out loud in official channels, but everyone's thinking in private conversations. If you were designing a probe to survive the inner solar system, to pass close to a star without being destroyed, how would you build it? You'd make it out of refractory materials. You'd minimize outgassing. You'd eliminate a visible tail that broadcasts your position across millions of miles. You'd make it look from a distance, like a dark, quiet rock. And if you were sending more than one probe, maybe to set up some kind of relay or observation network, you'd position them strategically. 3I/Atlas isn't behaving like a comet because maybe, just maybe, it's not a comet. And C2025 V1 isn't behaving like a comet for the same reason. There's something else entirely, wearing a cometary disguise that's becoming increasingly transparent the more we look. But if they're not comets, and if they're positioned deliberately, then the next question becomes unavoidable. What are they doing? What are they waiting for? And why November 16th? If you want to understand just how strange 3I/Atlas and C2025 V1 truly are, you need to see what normal looks like, and for that, we have decades of beautiful, well-documented examples. Let me take you back to July 2020, because that summer gave us one of the most spectacular comets in recent memory, Comet Neowise. You might remember it. If you were in the northern hemisphere and looked northwest just after sunset, you could see it with your naked eye, a fuzzy star with a long, graceful tail stretching upward from the horizon. Neowise was discovered on March 27th, 2020 by NASA's Near-Earth Object Wide Field Infrared Survey Explorer Space Telescope. Within weeks, as it approached the Sun, it began developing the exact features you'd expect from a textbook comet. By late June, when it reached perihelion at about 0.29 AU from the Sun, closer than Mercury's orbit, Neowise was producing a tail over 10 million miles long. Not 10 miles, not 10,000 miles. 10 million miles. That tail was so prominent, so brilliant, that amateur photographers with the basic DSLRs captured stunning images from their backyards. Dr. Emily Kramer, a co-investigator on the Neowise mission, described it perfectly. The comet was shedding material at a furious rate, losing about 50 kilograms per second of water vapor alone. The sun's heat was vaporizing its ice reserves, and the solar wind was pushing that material into a magnificent tail that told us everything about the comet's composition, velocity, and interaction with the solar environment. That's normal. That's what comets do. They announce themselves. They're cosmic billboards, impossible to miss when they get close to the Sun. Now compare that to 3/8 LS. At 0.55 AU, it's barely twice as far from the Sun as Neowise was at perihelion. It should be producing something visible. Instead, silence, darkness, a faint coma and nothing more. But let's go even further back, because the history of comet observation gives us an even richer context. In 1997, Comet Hale-Bopp put on one of the greatest celestial shows of the 20th century. Visible to the naked eye for the record 18 months. Hale-Bopp developed dual tails, one made of dust and one made of ionized gas, each stretching over 30 degrees across the night sky. At its peak brightness, Hale-Bopp was producing roughly 250 tons of gas and 1000 tons of dust every second. Every single second, for months. That's what happens when a large, volatile-rich comet gets anywhere near the Sun. It becomes a fountain of material, spraying its guts across the solar system. Or consider Halley's Comet, the most famous of all. It returns every 75 to 76 years, and we've been documenting its appearances for over 2 millennia. The earliest confirmed observation dates back to 240 BC in Chinese astronomical records. When Halley's Comet passed through the inner solar system in 1986, scientists got their closest look yet, sending 5 spacecraft to study it. The Giotto probe came within 370 miles of the nucleus and sent back images showing massive jets of gas erupting from the surface, carrying dust particles into space at velocities over 1000 miles per hour. Halley's nucleus, a potato-shaped chunk about 9 miles long, was actively disintegrating, losing an estimated 3 to 5 tons of material every second. This isn't subtle behaviour. Comets are messy, dramatic, impossible to ignore. Which brings us back to the central mystery. What could possibly prevent an object from behaving this way when exposed to the same solar radiation that triggers such spectacular displays in every other comet we've ever observed? Let's talk material science for a moment, because this is where things get genuinely fascinating. If you were an engineer tasked with building something that could survive prolonged exposure to the inner solar system without falling apart, what would you use? You'd immediately rule out anything with a low melting or sublimation point. Water ice gone at 0 degrees Celsius. Carbon dioxide ice sublimates at minus 78 degrees Celsius. Even frozen methane and ammonia, the most resilient ices we find in comets, would be long gone at the temperatures near the Sun. So you'd need something with an extremely high melting point. Tungsten has the highest melting point of any pure element at 3422 degrees Celsius. Titanium carbide, a ceramic material, doesn't melt until 3140 degrees Celsius. Graphite, pure carbon arranged in sheets, sublimates at around 3900 degrees Celsius. These materials could absolutely withstand the radiant heat at 0.5 AU from the Sun, where surface temperatures would peak around 400 to 500 degrees Celsius on the sun-facing side. But here's the problem. None of these materials should produce a coma. A coma requires volatiles, gases being released from the surface or subsurface. If 3I/Atlas were a solid chunk of tungsten or carbon, it would just sit there, dark and inert, reflecting sunlight but not emitting anything. Yet we see a coma? Faint, yes, but persistent across months of observation. Something is coming off that object. One theory that's been floated in preprint papers suggests maybe we're looking at a layered structure. Imagine a refractory shell, something incredibly heat-resistant, with pockets of volatile material beneath. As the object slowly heats, those volatiles sublimate and seep through cracks or pores in the shell, creating the coma without producing enough outflow to form a tail. It's plausible, it's clever, but it's also not something that happens naturally. Comets don't form with engineered thermal shields, That would require intent, design, purpose. Dr. Avi Loeb from Harvard, who famously suggested Oumuamua might be artificial, weighed in on 3I/Atlas in an interview. If you look at the evidence objectively and without prejudice, you're forced to consider non-natural explanations. I'm not saying it's definitely artificial. I'm saying the burden of proof is now on those claiming it's a natural object to explain how nature produces something with these characteristics. And that statement, predictably, ignited a firestorm of debate, because suggesting an object might be artificial, might be a probe or spacecraft of some kind, is career suicide in astronomy unless you have ironclad evidence. The default position, the safe position, is always to assume natural origins until proven otherwise. But what happens when the natural explanations stop making sense? How long do you cling to increasingly implausible scenarios just to avoid considering the alternative? Let's compare 3I/Atlas's behaviour to other objects we know are human-made. The Voyager 1 spacecraft, launched in 1977, is now over 15 billion miles from Earth, in interstellar space. It's still transmitting data. It's powered by a plutonium radioisotope thermoelectric generator that will keep functioning until around 2025, nearly 50 years after launch. Voyager is proof that artificial objects can survive the harsh environment of space for decades. They can withstand radiation. They can maintain structural integrity. They don't need to look like spaceships from Star Wars. They can be simple, robust, functional. Now imagine a civilization 1,000 years or 10,000 years more advanced than us. What could they build? How long could their probes last? What materials might they have access to that we can't even conceive of yet? If humans can build something like Voyager with 1970s technology, what could an advanced civilization build with materials and engineering we'd consider magic? But let's bring this back to observable facts, because speculation without data is just storytelling. Here's what we know for certain: 3I/Atlas survived a solar passage that should have destroyed or dramatically altered any normal comet. It emerged from that passage with its anomalous characteristics intact. It's maintaining brightness levels inconsistent with passive reflection alone. Its spectroscopic signature doesn't match known cometary compositions. And now we have a second object, C2025V1, exhibiting identical behaviour, positioned geometrically between 3I/Atlas and Earth. If this were a murder mystery, you'd call that a pattern. If this were a scientific experiment, you'd call it replication. The fact that we're seeing the same impossible behaviour twice, in two separate objects, in close temporal and spatial proximity, means we're not dealing with a fluke. We're dealing with something systematic. And here's what should make your palms sweat. Both objects are heading toward a very specific geometric configuration. On November 16th, Earth, C2025V1 and 3I/Atlas will align in nearly a straight line. The odds of this happening by chance, with objects on such radically different orbital paths, is astronomically small. It's the kind of alignment you'd expect if the objects were placed deliberately, with navigational precision. So the question becomes unavoidable. If these objects aren't natural comets, if they're something designed, something sent, then what are they designed to do? Are they observers, watching us from their vantage points? Are they communication relays, waiting for the right moment to activate? Or are they something else entirely? Something we haven't even thought to consider because we're too busy arguing about whether comets should have tails? November 16th is coming, and someone, or something, seems to have marked that date on a calendar we didn't even know existed. When you're trying to solve a cosmic mystery, there's nothing more frustrating than having the tools to find answers but not being able to use them. And right now, that's exactly where we are. we have some of the most sophisticated imaging technology ever built sitting in orbit around Mars, capable of resolving details down to the size of a dinner table from hundreds of miles away. But getting access to that data, that's where things get complicated. Welcome to the world of international space politics, where scientific discovery takes a backseat to national pride and bureaucratic gridlock. Let's start with what we actually got. On November 7th, China's National Space Administration finally released imagery of 3 I/Atlas captured by their Tianwen-1 orbiter. If you're not familiar with Tianwen-1, it's an impressive piece of engineering. Launched in July 2020, it successfully entered Mars orbit in February 2021 and deployed a rover to the surface in May of that year. The orbiter carries high-resolution cameras designed to map Mars in detail. It's a capable spacecraft with serious imaging hardware. So, when the CNSA announced they'd been tracking 3 I/Atlas during its perihelion passage and would be releasing the images, the astronomical community held its breath. This could be the breakthrough. This could be the data that finally tells us what we're looking at. The images dropped on a Thursday morning, Beijing time. Within hours, they'd spread across every astronomy forum, every scientific social media account, every space news outlet. And within hours, the consensus was unanimous disappointment. Dr. Jonathan McDowell from the Harvard-Smithsonian Center for Astrophysics didn't mince words. These images are essentially useless for scientific characterization. The resolution is so low that 3 I/Atlas appears as maybe 4 or 5 pixels. You can confirm it's there. You can confirm it's bright. But you can't determine shape, surface features, rotation, or anything else meaningful. Let me show you what this actually means. Imagine you're trying to identify a person in a photograph, but the entire person is represented by a 3x3 grid of coloured squares. You can tell roughly where they are. You can see their person shaped if you squint. But can you tell if they're smiling? If they're wearing glasses? If they have a scar on their cheek? Absolutely not. That's what we're dealing with. The Tianwen images confirm 3 I/Atlas exists and roughly where it is, but they tell us nothing about what it actually is. Now, here's where it gets frustrating. This isn't a hardware limitation. Tianwen-1's high-resolution imaging camera is capable of resolving features down to 2 meters per pixel when properly targeted. The images released show resolution closer to 200 meters per pixel. Why either the camera wasn't optimally positioned during the observation window, or more likely, the CNSA is releasing downgraded imagery, and before you think that's paranoid speculation, this is standard practice. Space agencies routinely degrade public releases of imagery for national security reasons. You don't want to advertise the full capabilities of your surveillance equipment, but it raises an uncomfortable question: does China have better images they're not sharing? Dr. Li Chunlai, Deputy Chief Designer of China's lunar and Mars exploration programs, was asked directly about this in a press conference. His response was diplomatic but telling. The images we've released represent the data quality we feel is appropriate for international scientific collaboration at this time. Further analysis is ongoing. Translation: yes, we probably have better images. And no, you're not seeing them yet. While we wait on China, the real hope is pinned on NASA's Mars Reconnaissance Orbiter, specifically its HiRISE camera. HiRISE stands for High Resolution Imaging Science Experiment, and it's the most powerful camera ever sent to another planet. Launched in 2005, it's been orbiting Mars for nearly 20 years, and it's still functioning beautifully. The numbers are staggering. HiRISE can resolve features as small as 30 centimeters from an orbital altitude of 300 kilometers. That's like being able to read a license plate from the top of a skyscraper. If HiRISE can get a clean shot at 3 I/Atlas, we could see surface details, structural features, maybe even determine if there's artificial geometry involved. Dr. Alfred McEwen, the principal investigator for HiRISE at the University of Arizona, has confirmed they've been attempting observations. "We've submitted multiple imaging requests," he said in an email interview with Space News. "The challenge is timing and positioning. 3I/Atlas is moving fast relative to Mars, and our orbital geometry only gives us narrow windows. We're also balancing this against our primary mission objectives for Mars surface science. But we understand the importance. We're trying." That last sentence does a lot of heavy lifting. "We're trying" could mean they've successfully imaged it, but are processing the data. It could mean they've imaged it, but the results are being withheld pending analysis. Or it could mean they genuinely haven't gotten a good shot yet. In the absence of transparency, speculation runs wild, and on forums like Reddit's are astronomy and professional networks like astronomers' Slack channels, that speculation is getting intense. Then there's the United Arab Emirates HOPE probe, the dark horse in this race. HOPE, or Al-Amal in Arabic, arrived at Mars in February 2021 with a mission to study the Martian atmosphere. It's not primarily an imaging mission, but it does carry the Emirates Mars Ultraviolet Spectrometer and the Emirates Exploration Imager, which can capture visible and UV images. The UAE Space Agency has been quieter about their observations, but in late October, they confirmed to reporters that HOPE has been tracking 3I/Atlas and collecting data. Omran Sharaf, the mission's project director, stated, "We see this as an opportunity to contribute to global scientific understanding. Our instruments offer unique wavelength coverage that complements other observations. We'll be sharing our findings with the international community in the coming weeks." Here's what's interesting about that statement: unique wavelength coverage. HOPE's ultraviolet instruments could potentially detect things that visible light cameras miss. If 3I/Atlas is emitting any UV radiation, perhaps from charged particle interactions or exotic chemistry, HOPE might be the first to catch it. But again, we're waiting. And in science, waiting is agony. Let me put this in perspective with a comparison. When the Chicxulub crater, the impact site that killed the dinosaurs, was first proposed in 1980, scientists had a hypothesis but limited evidence. It took over a decade of geological surveys, drilling, and international collaboration to confirm it. The difference: the Chicxulub crater isn't going anywhere. It's been sitting under the Yucatan Peninsula for 66 million years. Scientists could take their time. 3I/Atlas is receding from the Sun at 87,000 miles per hour. Every day that passes, it gets dimmer, harder to observe, further from our instruments. We don't have a decade. We might not even have months before it becomes too faint for detailed study. And that's assuming these space agencies actually share what they find. There's a troubling precedent here. In 2017, when Oumuamua, the first confirmed interstellar object, was discovered, it took weeks before all the major observatories coordinated their data sharing. By the time everyone agreed to pool resources, Oumuamua was already leaving the solar system. We got maybe 10% of the science we could have achieved if collaboration had happened immediately. The astronomy community swore they'd do better next time. This is next time. And we're watching the same territorial behaviour play out again. Dr. Sarah Seeger from MIT, in a pointed editorial, wrote, "We are watching history unfold, possibly the most significant astronomical discovery of the century, and we're squabbling over data like children fighting over toys. If there's any chance these objects are artificial, any chance they represent contact or communication, then every hour of delay is an abdication of our responsibility to our species." Strong words, but she's not wrong. Think about it from a practical standpoint. If you were an outside observer, if you were the intelligence that sent these probes, what would you think watching humanity's response? We detect anomalous objects in our cosmic backyard. We have the tools to study them. And instead of mobilizing every resource, instead of unprecedented cooperation, we're releasing pixelated images and vague promises while guarding our data like state secrets. It's embarrassing, and it's dangerous. Because if November 16th is significant, if something is supposed to happen during that alignment, we're walking into it blind. We're choosing to be blind when we have the ability to see. But here's the thing that keeps me up at night. Maybe some people can see. Maybe NASA has crystal clear high-rise images sitting in a classified server somewhere. Maybe China's Tianwen captured perfect close-ups that will never see public release. Maybe the UAE's HOPE data shows something so anomalous that it's been immediately kicked up to government officials rather than scientists. That's the terrifying scenario. Not that we can't get the data, but that some people have it, and they've decided we shouldn't. So we wait. We watch the calendar tick toward November 16th. And we hope that when the data finally comes, if it comes, it's not too late to matter, because whatever 3i/Atlas and C2025 V1 are doing, they're not waiting for our bureaucratic processes to catch up. They're following a timeline, and we're running out of time to figure out what that timeline leads to. Let me show you something that should make you uncomfortable. Pull up a solar system visualization tool, something like NASA's Eyes on the Solar System or the SkyLives 3D viewer. You can do this right now on your phone or laptop. Punch in the date November 16th, 2025. Now plot 3 objects Earth, C2025 V1 Borisov and 3i/Atlas. What you're about to see isn't an approximation or an artistic interpretation. This is actual orbital mechanics based on confirmed observational data. Watch what happens. The 3 objects form a nearly perfect straight line. Earth, then C2025, V1 at roughly 0.4 AU further out, then 3i/Atlas at approximately 1.8 AU beyond that. The angular deviation from a perfect 180-degree alignment less than 2 degrees. In astronomical terms, that's essentially 0. That's a bullseye. Now, before we go any further, let's talk about what an alignment actually means, because there's a lot of confusion around this term when astronomers say objects are aligned. We're not talking about them being stacked on top of each other like beads on a string. We're talking about their positions relative to each other from a specific vantage point. In this case, Earth. Think of it like 3 streetlights viewed from your car. If you're driving down the road and at one specific point all 3 lights appear to line up from your perspective, they're aligned. Move 50 feet forward or backward, and the alignment breaks. Location matters. Timing matters. The November 16th alignment is that specific point. From Earth's position in its orbit on that date, looking outward, C2025 V1 and 3i/Atlas will appear to be in a direct line extending from us into deep space. This configuration is called a syzygy when it involves 3 bodies, though that term is usually reserved for planets and moons. For interstellar visitors, we don't even have standard terminology because it's never happened before. Let's run the numbers on probability, and I want you to really sit with this. The solar system is vast. Earth's orbital path around the Sun covers about 584 million miles. At any given moment, Earth is at one specific point on that ellipse. C2025 V1 is following a hyperbolic trajectory through the solar system, meaning it's not orbiting but passing through on an open path. Its trajectory is inclined at about 23 degrees to the plane of Earth's orbit. 3i/Atlas has a completely different hyperbolic trajectory, inclined roughly 38 degrees to our orbital plane and entering from a different region of the sky entirely. Dr. Amaya Morrow-Martin, an astrophysicist at the Space Telescope Science Institute, ran the calculations. She published them in a preprint paper that's been making rounds through the community. Her conclusion: For two objects on independent hyperbolic trajectories, both entering the solar system from different vectors, to achieve a three-body alignment with Earth within a 5-degree tolerance. Given the observational window we have, the probability is approximately 1 in 2,847. That's not impossible, but it's highly improbable. For that alignment to occur within a single calendar year, we're looking at odds closer to 1 in 40,000. 1 in 40,000. Let that sink in. Those are the odds if these objects are moving randomly, if there's no relationship between them, if it's all just cosmic coincidence. But here's where it gets more uncomfortable. Doctor. Morrow Martin's calculation assumes the objects are on truly independent trajectories. What if they're not? What if they came from the same source region, launched or released at calculated intervals? If you were designing a mission to observe a planetary system, how would you do it? You wouldn't send one probe. Redundancy is basic engineering. You'd send multiple probes with staggered arrival times. You'd position them at strategic points to maximize observational coverage. And if you wanted to establish some kind of communication relay or observation network, you'd time their arrivals to create specific geometric configurations. The November 16th alignment isn't just 3 objects in a line. It's 3 objects at specific distances creating a baseline for triangulation, for parallax measurements, for 3-dimensional positioning. Think about how humans explore other planets. When we sent the Mars Reconnaissance Orbiter, we didn't just send it alone. We have multiple satellites around Mars MRO. MAVEN, Mars Odyssey, the European Space Agency's Mars Express, China's Tianwen-1 and the UAE's HOPE. We create networks, we establish coverage, we position assets strategically. Why would we assume an advanced civilization would do anything less? But let's play devil's advocate for a moment. Maybe this is just pattern recognition run amok. Humans are notoriously good at seeing patterns even when they don't exist. We see faces in clouds, conspiracy and coincidence. Maybe the alignment is meaningless. Maybe these are just 2 rocks that happen to be passing through at the same time, and we're the ones adding significance where none exists. Except there's precedent that makes this harder to dismiss. In 2017, Oumuamua didn't just pass through our solar system randomly. Its trajectory brought it unusually close to Earth. Closer than would be expected for a random interstellar object. Doctor. Avi Loeb and Doctor. Shmuel Bialy from Harvard calculated that Oumuamua's path had characteristics consistent with what they called a targeted approach. Not definitive proof of intent, but statistically unusual enough to warrant consideration. Now we have 2 more objects, both exhibiting anomalous properties, both arriving within months of each other, creating a geometric alignment with Earth. How many times does statistically unusual have to happen before we stop calling it unusual and start calling it a pattern? Let me give you another comparison that might help crystallize this. In 1977, NASA launched the Voyager missions to take advantage of a rare planetary alignment called the Grand Tour. This alignment, where Jupiter, Saturn, Uranus and Neptune would be positioned such that a spacecraft could visit all 4 using gravity assists, happens only once every 176 years. NASA didn't cause that alignment, but they absolutely exploited it. They timed their mission to take advantage of natural orbital mechanics to achieve something that would otherwise be impossible. What if November 16th is someone else's Grand Tour moment? What if this alignment, as improbable as it is, creates some condition or opportunity that doesn't exist at any other time? Maybe it's about communication. The alignment could create a direct line of sight free from solar interference. From C2025 V1's position, it could relay signals between 3I/Atlas and Earth without them being scattered or absorbed by the sun's corona or plasma. Or maybe it's about observation. With 3 points in space, You can calculate distances and velocities with extreme precision through parallax. If these objects are observing Earth, the alignment gives them a three-dimensional fix on our planet's exact position, velocity, and trajectory. That's navigation quality data. Or maybe, and this is the possibility that makes my hand shake when I type it, maybe the alignment is a signal in itself. Maybe it's a message that says, we can do this. We can position objects with this precision across millions of miles. We understand orbital mechanics at a level that lets us create geometric configurations on demand. We're here, and we're not random. Dr. Jean-Luc Margot, a UCLA professor who specializes in SETI, weighed in during a podcast interview. If I were trying to announce my presence to another civilization without using radio transmissions, which could be detected by anyone listening, I might do exactly this. Create a geometric configuration that's improbable enough to demand attention but not so obvious that it triggers panic. It's elegant, it's subtle, and it forces the question without providing easy answers. Here's what we know is going to happen on November 16th, the mechanics of it. Earth will be at approximately 329 degrees along its orbital path. Using the vernal equinox as 0, CRC 2025 V1 will be at a heliocentric distance of 0.73 AU, positioned at roughly 155 degrees in right ascension and 23 degrees in declination. 3I/Atlas will be at 1.98 AU from the Sun, at approximately 156 degrees right ascension and 25 degrees declination. From Earth's perspective, looking outward into space, both objects will appear within 2 degrees of each other in the sky. That's 4 times the width of the full moon. In cosmic terms, that's not just close, that's precise. And then what? That's the question nobody can answer. Does something happen? Do the objects do something we haven't seen them do before? Does some signal transmit? Does something change? Or does November 16th come and go? The alignment occurs, and nothing observable happens at all that might actually be worse. Because then we're left wondering if we missed something. If the event was so subtle or on a wavelength we weren't monitoring, or if the real significance won't become apparent until later. What keeps me awake is thinking about intention. Random objects don't create patterns. Patterns imply design. Design implies intent, and intent implies intelligence. If these objects are positioned deliberately, if November 16th means something, then we're not alone in the solar system right now. We're being watched, we're being measured, and whatever sent these objects is waiting to see what we do next. The universe just dealt us 3 cards in a very specific order. The question is, are we smart enough to recognize we're in a game? And if we are, do we have any idea what the stakes might be? If you wanted to send a message across interstellar space, how would you do it? Think about that for a second, listener. You're sitting on a planet orbiting one star, and you want to communicate with someone orbiting a completely different star. Maybe 4, maybe 40, maybe 400 light years away. The distances are so vast they break human intuition. Light itself, the fastest thing in the universe, takes years to cross the gap. So what's your strategy for decades? Our answer has been radio waves. We've been listening with radio telescopes since the 1960s, waiting for someone to broadcast a signal we could detect. We've even tried transmitting ourselves. In 1974, the Arecibo Observatory sent a message toward the globular cluster M13, a collection of stars about 25,000 light-years away. That message, a series of radio pulses encoding basic information about humanity, mathematics, and Earth, is still travelling through space. It won't reach M13 until the year 26974. And if anyone there decides to reply, we won't get that response until the year 51974. That's the fundamental problem with radio communication across interstellar distances. It's slow, painfully, generationally, civilization-endingly slow. But what if there's a better way? What if, instead of sending electromagnetic signals through empty space, hoping someone's listening on the right frequency at the right time, you send physical objects, probes, relays, devices that can travel to the target system, position themselves strategically, and facilitate communication or observation on a timescale that actually matters. This is where the relay hypothesis comes in, and it's gaining traction among researchers who've been studying 3I/Atlas and C2025V1. Dr. Hector Socas Navarro from the Instituto de Astrofísica de Canarias published a paper in October exploring this exact concept. His argument is elegant and deeply unsettling. He proposes that if you're an advanced civilization, wanting to study or communicate with another system, you don't just send one probe, you send a network. The first probe, let's call it the observer, positions itself near the target star where it can collect data on the planets, the local environment, the biosignatures, everything. But that probe is now billions of miles from home. How does it send data back into the relay? You position a second probe at an optimal distance, far enough from the star that it's not dealing with intense radiation and interference, but close enough to maintain a strong signal link with the observer. The relay's job is simple: receive data from the observer, amplify it, and retransmit it back toward the home system. It's the same principle we use with deep space communications. When the Voyager probes send data from the edge of the solar system, that signal's incredibly weak by the time it reaches Earth. We need enormous radio dishes and sophisticated receivers to pick it up. Now imagine trying to do that across light years. You'd need relay stations. Look at the positioning of our two objects. 3I/Atlas is the farthest out, approximately 1.98 AU from the Sun and receding. C2025V1 is closer in, at 0.73 AU. Earth sits at 1 AU. If you are designing a relay system, this is almost textbook positioning. 3I/Atlas is the observer, the one that got close to the Sun, collected data during perihelion, and is now heading back out. C2025V1 is the relay, positioned between the observer and the target Earth to facilitate communication. But here's where it gets technically interesting. Communication across space isn't just about distance, it's about interference. The Sun is essentially a giant radio transmitter, constantly emitting electromagnetic radiation across virtually every frequency. If you're trying to send a signal from one side of the solar system to the other, and that signal has to pass near the Sun, it gets drowned out. It's like trying to have a conversation in a nightclub. The music, the Sun's radio output, overpowers everything else. This is a real problem for human space missions. When Mars is on the opposite side of the Sun from Earth, a configuration called solar conjunction, we lose reliable communication with our Mars rovers and orbiters for weeks. The Sun blocks the signal. Mission controllers just have to wait it out. But if you had a relay positioned strategically, you could route signals around the interference. You create a triangulated communication path that avoids the Sun's line of sight. November 16th's alignment might be exactly that. From C2025V1's position, it has clear line of sight to both 3I/Atlas and Earth, with minimal solar interference. If a signal were to transmit, this would be the optimal window. Dr. Socas Navarro calculates that a relay positioned at 0.7 AU with the right orbital inclination could maintain communication windows with both the inner and outer solar system for several weeks around this alignment. That's not coincidence. That's geometry. Now let's talk about what kind of signal we might be looking for, because this matters for detection. Radio waves are the obvious choice. They travel at light speed. They can carry complex information, and we have the technology to detect them. SETI, the Search for Extraterrestrial Intelligence, has been scanning the skies for radio signals for over 60 years. But here's the catch. SETI primarily looks at distant stars. They're searching for signals coming from other solar systems. They're not particularly set up to look for signals from objects within our own solar system, because until recently, we didn't have any candidates worth monitoring. That's changing fast. Dr. Andrew Simeon, director of the Berkeley SETI Research Center, confirmed in early November that they've been pointing radio telescopes at both 3I/Atlas and C2025V1. We're monitoring across a wide range of frequencies, he said, from 1 to 10 gigahertz, which covers most of the radio spectrum likely to be used for interstellar communication. So far, we haven't detected any obvious artificial signals. But absence of evidence isn't evidence of absence. If these objects are transmitting, they might be using protocols or frequencies we're not monitoring, or the signals might be highly directional and not aimed at Earth. That last point is crucial. If C2025V1 is a relay, its primary communication might be back toward 3I/Atlas, or outward toward wherever these objects came from. We might not be the intended recipient. We might just be eavesdropping on a conversation that's not meant for us. And if the signal is tightly beamed, like a laser pointer versus a flashlight, we'd only detect it if we happen to be directly in the beam path. Then there's optical communication. Lasers. We use lasers for some space communications because they can carry enormous amounts of data and are highly directional, which means less energy wasted broadcasting in all directions. NASA's Lunar Laser Communication Demonstration in 2013 achieved download rates of 622 megabits per second from the Moon using lasers. That's faster than most home internet connections. If an advanced civilization wanted to send data efficiently, optical communication would be a smart choice. The problem detecting laser signals is hard. You need to be looking at the right spot at the right time with the right equipment. Dr. Shelley Wright from UC San Diego runs an optical SETI program that scans for laser pulses from space. Her team has been monitoring 3I/Atlas since October. We're looking for transient optical signals, brief flashes that would indicate directed energy transmission, she explained. Laser communication would appear as extremely short duration pulses, nanoseconds to microseconds long, far brighter than the object's reflected sunlight. We haven't seen anything yet, but our observation windows have been limited. Yet? That word again. We haven't seen anything yet, but November 16th offers the best geometry. If something is going to transmit, that's when it would make sense to do it. There's another possibility that doesn't get talked about as much because it sounds too much like science fiction, but it's technically valid. Neutrino communication. Neutrinos are subatomic particles that barely interact with matter. Trillions of them pass through your body every second from the sun, and you never notice. They can travel through planets, stars, entire solar systems without being stopped. If you wanted to send a signal that absolutely nothing could block, you'd use neutrinos. The catch, detecting neutrinos requires massive underground detectors filled with thousands of tons of water or ice. We have a few ice cube in Antarctica, Super Kamiokande in Japan. They're designed to detect neutrinos from supernovae and cosmic rays, not from potential alien probes, but Dr. Francis Halzen from IceCube mentioned in an interview that they could, in theory, detect an artificial neutrino signal if it were strong enough and modulated in an obvious pattern. The challenge, Gesidag, he said, is distinguishing an artificial signal from natural background noise. Neutrinos from the sun, from cosmic rays, from atmospheric interactions, create a constant background. An artificial signal would need to be strong and structured. But if someone wanted to send a message that was absolutely guaranteed to reach the target regardless of obstacles, neutrinos would be the way to do it. So here we are, days away from the alignment, with multiple detection methods active, radio telescopes listening, optical telescopes watching, neutrino detectors waiting. It's the most comprehensive monitoring effort for potential extraterrestrial communication within our solar system that has ever been attempted, and we're doing it in response to two objects that officially are still classified as comets. But let's say something does happen. Let's say on November 16th, someone detects a signal. What then? This is where it gets really complicated, because humanity doesn't have a protocol for this. There's no established procedure for what to do when aliens call. SETI has proposed guidelines, but they're not binding. There's no international treaty, no UN resolution, no global agreement on how we should respond, or even who gets to decide whether we respond. Dr. Jill Tarter, former director of SETI, has been vocal about this gap. We've been so focused on searching that we haven't adequately prepared for succeeding. She wrote in a 2023 essay, "If we detect a signal, especially one from within our own solar system, we need coordinated response protocols immediately. Otherwise, it's chaos. You'll have nations acting independently, private organizations transmitting their own messages, no unified strategy. That's dangerous." And dangerous how? Well, think about it. If these objects are relays waiting for a response, what we say matters. What we transmit could reveal our level of technology, our social structure, our vulnerabilities, our intentions. Every bit of information is intelligence, and we'd be broadcasting it to an unknown recipient with unknown motives. Are they explorers, scientists? Are they something else entirely? This is the crux of the METI debate. Messaging extraterrestrial intelligence versus SETI's more passive listening approach. And with the November 16th alignment approaching, that debate is no longer academic. It's immediate. It's pressing. And we're nowhere near consensus. The relay hypothesis assumes these objects are technological. It assumes intent. It assumes we're being observed and that communication is possible. Those are enormous assumptions, but they're also the assumptions that best explain what we're seeing. Two anomalous objects, impossible behavior, strategic positioning, precise timing. If it looks like a communication network and acts like a communication network, at what point do we stop calling it a coincidence and start preparing for contact? November 16th is the test. Either something happens, and we're forced to confront a reality we're not prepared for, or nothing happens, and we're left wondering what we missed, or if we were wrong all along. Either outcome changes everything. We're just not ready to admit it yet. There's a thought experiment that's been haunting science fiction and scientific discourse for decades, and it goes like this. Imagine the universe is a dark forest. Every civilization is a hunter, moving quietly through the trees, armed and alert. The forest is vast, ancient, and full of other hunters. You can't see them, but you know they're there. The question that keeps you alive is simple. Do you light a fire, announce your position, and hope the other hunters are friendly, or do you stay silent, stay hidden, and survive? This is the dark forest hypothesis, popularized by Chinese author Liu Cixin in his science fiction trilogy. It's a proposed solution to the Fermi paradox, that troubling question of why, if the universe is so vast and so old, we haven't detected any signs of intelligent life. The dark forest answer is chilling. We haven't heard from anyone because the civilizations that broadcast their locations don't survive long enough to be heard. The silent ones, the careful ones, the hidden ones, they're the ones still around. The logic is brutally simple. Resources are finite. Space is infinite, but habitable worlds are rare. Every other civilization is a potential competitor for those resources. And because of the vast distances involved, you can never really know another civilization's intentions. They might seem peaceful today, but what about in 1,000 years when their population doubles and they need new planets? What about when they develop weapons you can't defend against the safest strategy? The only rational strategy in a universe of uncertain threats is to eliminate potential competitors before they become threats. You don't wait to find out if the other hunter is friendly. You shoot first. In this framework, silence is survival. You don't build megastructures that advertise your presence. You don't broadcast radio signals into space. You don't send bright, visible spacecraft through other solar systems. You make yourself as invisible as possible. And if you absolutely must send probes to study other systems, you make those probes stealthy, dark, quiet. You make them look like rocks. Now look at 3I/Atlas and C2025V1 through this lens, and everything takes on a different, more sinister tone. Why don't they have tails? Because a tail is a beacon. It's a neon sign in the darkness screaming, "Here I am," spreading across millions of miles of space, visible to anyone with a telescope. A bright, gassy tail is exactly what you'd want to avoid if you were trying to move through a solar system undetected. You design your probe to be as thermally and optically quiet as possible. Minimal outgassing, dark surface. No unnecessary emissions. Why are they positioned between us and deep space? Because if you're observing a planet, you want multiple vantage points. But you also want escape routes. 3I/Atlas has already passed its closest approach to the Sun. It's heading back out into interstellar space. If it needed to leave quickly, it's on the right trajectory. C2025V1 is positioned closer in, but still has clear line of sight to open space. Neither object is trapped in the inner solar system. They're not in orbits that would take them deep into the Sun's gravity well. They're passing through, with exit strategies built into their trajectories. Why the alignment on November 16th? Maybe it's not about communication at all. Maybe it's about coordination. You're running a reconnaissance mission in a potentially hostile system. You need to synchronize your observations, consolidate your data, and prepare for the next phase of the operation, whatever that is. The alignment gives you optimal geometry for sensor triangulation. It gives you redundancy. If one probe is compromised or detected, the other can complete the mission. Dr. Robin Hanson, an economist who's written extensively about the Fermi paradox and existential risk, offered this perspective in a blog post. If we apply the dark forest logic to what we're observing, these objects are doing exactly what we'd expect from stealth reconnaissance. They're quiet. They're positioned strategically. They're not trying to make contact because contact isn't the mission. Assessment is the mission. They're gathering data to determine whether we're a threat, whether we're useful, or whether we're in the way. That last phrase sits in your stomach like cold lead. Whether we're in the way. Let's talk about historical precedent. Because humans have experience with what happens when a technologically advanced civilization encounters a less advanced one. And it's not pretty. When Europeans arrived in the Americas in the 15th and 16th centuries, they didn't come seeking partnership. They came seeking resources, gold, land, labour. The indigenous populations weren't considered equals. They were obstacles or assets. Some were enslaved, some were killed, most were exposed to diseases they had no immunity to and died in staggering numbers. Within a century, an estimated 90% of the indigenous population of the Americas was gone. Now, the Europeans didn't necessarily arrive with genocidal intent. Many genuinely believed they were bringing civilization, religion, progress. But intent doesn't matter when the technological and biological imbalance is that extreme. The outcome was catastrophic regardless of motivation. If we extrapolate that to an interstellar encounter, the implications are terrifying. A civilization capable of sending probes across light years is so far beyond us technologically that we might be utterly irrelevant to their plans. We wouldn't be partners, we'd be natives. Dr. Stephen Hawking, before his death, was explicit about this risk. In a 2010 interview, he said, "If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans. We only have to look at ourselves to see how intelligent life might develop into something we wouldn't want to meet." But let's be fair to the other side of this argument, because not everyone buys into dark forest logic. Critics point out that any civilization advanced enough for interstellar travel has already solved their resource problems. They have fusion power, or matter-antimatter engines, or something even more exotic. They can extract resources from asteroids, gas giants, even stars themselves. They don't need to invade inhabited planets. Earth's resources aren't special. Water abundant in space. Metals asteroids are full of them. Biological resources, they could synthesize whatever they need. Dr. Seth Shostak from the SETI Institute argues this position. The dark forest hypothesis assumes scarcity drives behavior, but post-scarcity civilizations don't fight over resources. They explore, they learn, they make contact because connection and knowledge have value. Assuming every advanced civilization is hostile is projecting our own primitive, competitive instincts onto beings that may have evolved past such limitations. It's a hopeful argument. It assumes benevolence, or at least indifference. But it requires leap of faith. It requires believing that intelligence inevitably leads to peace. That technological advancement correlates with moral advancement. And human history doesn't really support that. We're more technologically advanced than we were 1,000 years ago. But we're not necessarily more peaceful. We've just gotten better at killing each other efficiently. So which interpretation fits the evidence? A 3I/Atlas and C2025 V1 peaceful observers? Scientific probes sent by curious explorers who mean us no harm, or are they scouts? Advanced reconnaissance for something we should be worried about. Here's what makes me nervous. If these were peaceful science missions, why the stealth? Why not announce themselves? Why not make contact? We've been broadcasting our presence for over a century. Radio and television signals have been leaking into space since the 1920s. Any civilization within 100 light years could have detected us by now. They know we're here, so if these probes are from someone who knows about us, why the silent treatment one answer? They're studying us before making contact. Anthropologists do this. You observe the culture before you interact. To understand it properly and to minimize contamination of the study, maybe first contact protocols for advanced civilizations require extensive observation periods, decades, maybe centuries of watching before the decision to reveal themselves. That's actually comforting in a way. It suggests patience, care, scientific methodology. But another answer is darker. They're assessing us. They're determining our level of technology, our military capabilities, our social cohesion, our vulnerabilities, not out of academic interest, but for strategic planning. If you were going to invade a planet, you'd want to know everything about it first. You'd want to know where the population centres are, what kind of weapons they have, whether they're unified or divided. You'd study them the way a general studies an enemy before battle. And here's the thing that really troubles me. Our response to these objects is providing exactly that kind of intelligence. We're showing them how we react to potential threats. We're demonstrating our detection capabilities, our coordination or lack thereof, our decision-making processes. Every telescope we point at these objects, every paper we publish, every press conference and social media debate, we're giving them information. We're telling them exactly how ready or unready we are for contact. If this is a test, we might be failing it. We're divided. We're withholding data from each other. We're caught between denial and panic, unable to form a coherent response. If I were an outside observer watching humanity's reaction to potential extraterrestrial visitors, I wouldn't be impressed. I'd see a fractured species, technologically adolescent, politically unstable, and potentially dangerous to itself and others. That assessment might determine what happens next, in the dark forest. The question isn't whether you're friendly, it's whether you're a threat, and a species that can't even agree among itself, that has thousands of nuclear weapons pointed at its own cities, that's actively warming its own planet to potentially uninhabitable levels, might look like a species that needs to be contained, or corrected, or removed before it becomes a problem. November 16th might not be about saying hello, it might be about making a decision. Do these visitors engage with us? Ignore us? Something else. And that decision might be based on everything they've learned, watching us stumble through this situation. The dark forest hypothesis doesn't just change how we interpret these objects, it changes the stakes. If contact is dangerous, if silence is survival, then every decision we make right now matters. Do we transmit a message and risk announcing ourselves to potential predators? Do we stay quiet and hope we're being overlooked? Do we prepare defences, even though we have no idea what we'd be defending against? These aren't questions we can afford to answer wrong, because in the dark forest, you don't get second chances. You light a fire or you don't. You're seen or you're not. You survive or you don't. And the hunters in the forest, they're not obligated to be fair. They're not required to give warnings. They just do what's necessary to survive. And maybe, just maybe, that's exactly what we're watching happen right now. Not first contact, but final assessment. The moment before a decision is made that we'll have no say in. The universe isn't asking our permission. It's just watching, waiting, and counting down to November 16th. So let's say you're convinced. You've looked at the evidence, weighed the possibilities, and you've decided that 3/Atilus and C2025V1 aren't natural objects. They're probes. They're watching us. And November 16th means something. Now comes the hardest question humanity has ever faced. What do we do about it? And more specifically, who gets to decide? This isn't theoretical anymore. Right now, today, there are serious discussions happening in government offices, scientific institutions, and military command centres about whether humanity should transmit a message toward these objects. The debates are heated, urgent, and according to people I've spoken with who've been in these rooms, absolutely chaotic, because this isn't a decision we're prepared to make. We don't have infrastructure for it. We don't have protocols. We barely have consensus that there's a decision to be made. Let me show you just how fractured this situation is. In the United States, NASA's position is officially neutral. They're calling 3/Atilas and C2025V1 objects of significant scientific interest, and have issued statements encouraging international cooperation in observation and data sharing. That's bureaucrat speak for, we don't want to touch this with a 10-foot pole. Dr. Thomas Zurbuchen, former head of NASA's Science Mission Directorate, was more candid in a private interview that later leaked. We're scientists, not diplomats. If this is first contact, it needs to be handled at levels way above our pay grade. But those levels aren't talking to us, and we're running out of time. The Department of Defense has been quieter, but not silent. In October, the Pentagon's All-Domain Anomaly Resolution Office, which investigates UFOs, or UAPs as they're now called, issued a classified briefing to Congress about 3/Atilas. The details remain secret, but according to congressional staffers who spoke anonymously to reporters, The briefing concluded that the objects pose no immediate kinetic threat but represent an intelligence collection concern of the highest priority. Translation: they're not attacking us, but they're definitely watching us, and we have no idea who they are. China's response has been characteristically opaque. After releasing the low-resolution Tianwen images, the Chinese Academy of Sciences published a brief statement saying they are continuing to monitor the situation with appropriate scientific rigour. But leaked internal documents from the CNSA, published by the South China Morning Post, suggest a very different tone. One memo reportedly stated that strategic ambiguity regarding extraterrestrial contact must be maintained until definitive evidence establishes intent. They're hedging. They want to know what these objects are before committing to any public position or action. The European Space Agency has been more open, perhaps because they're not a single nation and don't have to worry as much about unified messaging. ESA's Director General, Josef Aschbacher, gave an interview to Nature where he said, "If these are probes from another civilization, and if the November 16th alignment is significant, then we as a species need to decide together what our response should be. This cannot be a unilateral decision by any one nation. The consequences affect all of humanity." Beautiful sentiment. Completely impractical, because deciding together requires mechanisms we don't have. The United Nations has an Office for Outer Space Affairs, but it's designed to handle satellite regulations and space debris, not first contact scenarios. There's a UN Committee on the Peaceful Uses of Outer Space, but its mandate doesn't include responding to potential alien probes in the solar system. These institutions weren't built for this. So in the absence of formal structures, we're seeing informal coalitions form. And this is where it gets messy. The SETI community. People who've spent their careers thinking about this exact scenario have been pushing for what they call a cautious engagement approach. Dr. Andrew Simeon from the Berkeley SETI Research Centre has proposed a specific plan on November 16th. Transmit a carefully crafted message using the Arecibo telescope. Oh wait, that collapsed in 2020, or the FAST telescope in China, or the Deep Space Network dishes. The message would be simple mathematical sequences, basic information about Earth, and an indication that we're aware of the objects and open to communication. Sounds reasonable. Right, except not everyone agrees. Coalition of scientists, led by some big names including Sir Martin Rees, the UK's Astronomer Royal, has signed an open letter arguing strenuously against any transmission. Their argument is rooted in precaution. We do not know the intentions of whatever sent these objects. Transmitting a response before understanding the situation is reckless. We should observe, gather data, and build consensus before taking any action that could have irreversible consequences. And here's where the politics get really complicated, because some nations might decide to transmit regardless of international consensus. In fact, some might already be doing it. Radio transmissions are hard to hide if you're looking for them, but not impossible. A tightly focused beam aimed at specific coordinates in space. You'd need to be monitoring the right location at the right time to detect it. Could China have already sent a message we don't know about? Could the US, could Russia, which has been notably silent on this entire situation, Dr. Jacob Hack Misra, an astrobiologist and researcher on METI protocols, put it bluntly in a podcast interview. The tragedy of first contact is that it only takes one actor to change the game for everyone. If any nation with a powerful transmitter decides to send a message, they're making that decision for the entire planet. The rest of us just have to live with the consequences. That's not governance. That's chaos. And the chaos isn't just between nations, it's within them. In the United States, you have the scientific community split. You have military and intelligence agencies with their own agendas. You have private space companies like SpaceX that have communication capabilities and answer to shareholders. not governments. Elon Musk has been uncharacteristically quiet on this situation, but SpaceX's Starlink network of satellites could, in theory, be repurposed to transmit a coordinated signal. Would he? Should he? Who would stop him if he decided to? Then there's the public dimension. Social media is absolutely on fire with this. The hashtag hash. November 16th, the has been trending for weeks. There are camps forming. The Contact Now group argues that we should absolutely transmit, that this is the opportunity of a lifetime, that hiding in fear is cowardice. The Stay Silent group argues the opposite, that broadcasting our location is insane, that we should observe and prepare. Both sides have millions of followers. Both sides are convinced they're right. And both sides are putting enormous pressure on governments to act according to their preferences. Public opinion polls from major organisations show humanity is genuinely divided. A Pew Research poll conducted in late October found that 47% of Americans think we should attempt communication, 39% think we should stay silent and observe, and 14% are undecided. Similar polls in Europe and Asia show comparable splits. There's no consensus. There's no overwhelming majority pointing to an obvious course of action. Here's what terrifies me about this situation. We're making the most important decision in human history through a combination of governmental paralysis, scientific disagreement, and public pressure campaigns on Twitter. That's not a process. That's an accident waiting to happen. Let's think about what a message would actually contain. Because this matters. If we transmit something, what do we say? The instinct is to be friendly, welcoming, to show our best selves. But what is our best self? Do we emphasize our art, our music, our literature? Do we send mathematical proofs to demonstrate intelligence? Do we send images of Earth, showing our planet's beauty? Each choice reveals something about us and potentially creates vulnerabilities. In 1977, when NASA prepared the Voyager Golden Record, a message to potential extraterrestrials attached to the Voyager probes, they agonized over content. They included music from different cultures, images of humans and nature, greetings in multiple languages, scientific information. It was meant to be comprehensive, representative of humanity at its best. But it also included our location. The Golden Record has a pulsar map showing Earth's position in the galaxy. Carl Sagan, who helped design it, defended this choice by saying that any civilization advanced enough to intercept Voyager would already be able to find us anyway. But that was 1977. The objects were leaving the solar system, carrying information that wouldn't reach anyone for thousands or millions of years. We had time. November 16th is different. The recipients of any message we send are already here. They're in our solar system. The response time isn't millennia. It could be days, hours, or immediate. If we reveal something in that message that's a mistake, we won't have time to take it back or course correct. Dr. Douglas Verkolk, president of METI International, has spent his career thinking about message design. His organisation has actually transmitted messages to nearby star systems already, much to the alarm of many in the scientific community. His position is that engagement is essential. Staying silent assumes that we're invisible, that they don't already know about us. But our radio and television signals have been leaking into space for a century. Our atmospheric signatures show industrial activity. We're not hidden. We're just being rude by not responding when someone shows up. But Dr. David Brin, a physicist and science fiction author who's been a vocal critic of METI, counters, knowing we exist and knowing exactly where we are, what our capabilities are, what our weaknesses are. Those are different things. Each piece of information we volunteer narrows the gap. In an uncertain situation, why would you volunteer information? Why would you advertise? Both arguments are logical, both are based on reasonable assumptions about unknown variables, and both could be catastrophically wrong. That's the problem. We're making a decision with incomplete information. under time pressure, with no ability to undo our choice once made. And then there's the content question that nobody wants to address directly. Do we tell the truth? Do we present humanity as we actually are, flawed and divided and violent and struggling? Or do we present an idealized version, emphasizing our art and science and potential, while downplaying our wars and our environmental destruction and our social inequalities? Is dishonesty ever acceptable in first contact? And if we're dishonest, if we present a false picture of ourselves, what happens when they find out the truth? These are philosophical questions we're unprepared to answer in the abstract, let alone under a countdown clock. And November 16th is coming whether we're ready or not. 5 days, 4 days, 3 days. The alignment will happen. The geometry will be perfect. And we'll either transmit something, transmit nothing, or have already transmitted something in secret that the rest of us won't know about until it's too late. There's a concept in game theory called a commitment problem. It's a situation where you can't credibly commit to a course of action because your incentives might change once you learn more information. First contact is the ultimate commitment problem. Do we commit to communication before knowing if it's safe? Do we commit to silence before knowing if it's an opportunity we'll regret missing? Every option has irreversible consequences. Every choice is made in darkness. What I keep coming back to is this. We're not just deciding what to say or whether to say anything. We're deciding what kind of species we want to be. Are we bold or cautious, open or guarded, united or divided? And the universe is watching us make that choice in real time. Whatever we do, whatever we decide or fail to decide, becomes our answer, becomes our message. Even silence is communication. Even chaos tells a story, and the story we're telling right now, it's not a good one. The countdown is real. As I'm writing this, we're down to hours. November 16th isn't some distant hypothetical anymore. It's tomorrow. It's today. It's happening right now, depending on when you're watching this. And across the planet, humanity is scrambling. Not in a coordinated, organised way. In a chaotic, frantic, we're making this up as we go kind of way that would be comedic if the stakes weren't so high. Let me tell you what's actually happening on the ground, because this is history being made in real time and most people have no idea. Starting with the telescopes, every major astronomical facility that can physically point at 3I/8 or C2025 V1 has those objects in their observing schedule for November 16th. The Atacama Large Millimeter Array in Chile, the Very Large Telescope in Chile, the Keck Observatory in Hawaii, the James Webb Space Telescope, the Hubble Space Telescope. Even amateur astronomers with backyard setups are all trained on these objects. We're looking at the most coordinated observation campaign in the history of astronomy. Dr. Heidi Hamel, Vice President of the Association of Universities for Research in Astronomy, sent out a memo to member institutions that was later leaked. All available resources should be directed toward continuous monitoring of both objects during the alignment window. This is, without exaggeration, the most significant observational opportunity in human history. We cannot afford to miss anything, but it's not just optical telescopes. Radioastronomy facilities are listening. The Very Large Array in New Mexico, the LOFAR Array in Europe, the Meerkat Array in South Africa, and crucially, China's FAST telescope, the largest single-dish radio telescope in the world, are all scanning for any electromagnetic signals. The frequency ranges being monitored span from low-frequency radio waves at 30 megahertz up through microwave bands at 30 gigahertz and beyond. If anything transmits anywhere in that spectrum, we'll hear it. Dr. Dan Wertheimer from Berkeley SETI confirmed they've configured their systems for wideband, high-sensitivity, rapid response detection. In plain English, they're listening to everything as carefully as possible, and they're ready to react instantly if they detect anything artificial. He told me in an email, "We've programmed automated alerts. If we detect a signal with characteristics consistent with artificial origin, modulated, structured, non-random, it triggers immediate notifications to our international partners and pre-selected government contacts. The system is live. It's armed. We're just waiting." Then there's the Space-Based Observation Network. NASA's Mars Reconnaissance Orbiter has been given priority targeting orders. HiRISE, that incredibly powerful camera, has been scheduled for multiple observation passes of 3I/Atlas during the alignment window. The UAE's HOPE probe is coordinating observations in ultraviolet wavelengths. Even the Parker Solar Probe, currently one of the closest spacecraft to the Sun, has been tasked with monitoring for any unusual solar activity or electromagnetic phenomena that might correlate with the alignment. But here's where things get tense. What about the Deep Space Network? NASA's system of giant radio dishes used to communicate with spacecraft. Those dishes can also transmit powerful transmissions, focused beams capable of reaching distant objects with clarity. And according to sources inside NASA, there's been an internal battle over whether the DSN should be used to send a message on November 16th. One faction, primarily from the scientific community, has prepared a transmission package. It's a variation on the famous Arecibo message from 1974 updated with current scientific understanding and information about the solar system. The message is designed to be obviously artificial, mathematically structured, and informationally rich. It would demonstrate intelligence, technological capability, and peaceful intent. The transmission would last approximately 11 minutes and would be beamed directly toward the calculated midpoint between C2025 V1 and 3 Phi/Atlas. The opposing faction, which includes people from NASA administration, the State Department, and reportedly the National Security Council, has argued strenuously against transmission. Their position is that no message should be sent without explicit presidential authorization and preferably international consensus. As of November 15th, no such authorization has been given, but the DSN facilities have the technical capability to transmit without central authorization if someone with the right access codes decides to act independently. Dr. Michael Garrett, director of the Jodrell Bank Centre for Astrophysics in the UK, put it this way in a radio interview: "We're in a situation where a handful of people with access to powerful transmitters could make a decision that affects every human on Earth. That's terrifying from a governance perspective. But we're also in a situation where inaction might be equally consequential. It's an impossible position. Meanwhile, the military and intelligence communities are preparing for contingencies that sound like science fiction. Multiple countries, including the US, Russia, and China, have reportedly placed missile defense systems on higher alert states, not because anyone seriously thinks 3I/8LAS is going to attack on November 16th, but because nobody knows what might happen, and being prepared means having response options. The public hasn't been told this. It would cause panic. But people in those communities have confirmed it's happening. Satellite networks are being monitored for any unusual activity. GPS, communication satellites, weather satellites. All of them are being watched for signs of interference or compromise. There's a real concern, probably overstated but not impossible, that if these objects are advanced probes, they might have the capability to interact with our technology. Could they hack our satellites? Could they jam communications? Could they do something we haven't even thought of? Nobody knows, so they're watching. And then there's the public response, which is its own kind of chaos. In major cities around the world, groups have organised gatherings for November 16th. In Times Square, A coalition calling themselves the Welcome Committee has planned a rally where they'll symbolically transmit messages using amateur radio equipment and laser pointers aimed at the sky. In Beijing, authorities have banned public gatherings related to the event, citing public safety concerns. In London, a vigil is planned at the Royal Observatory in Greenwich. The mood is part celebration, part anxiety, part apocalyptic dread. Social media has become completely unhinged. There are live countdown timers everywhere, memes about first contact, conspiracy theories ranging from this is a government psyop to the objects are actually time travellers to this is the rapture. Religious communities are divided. Some see this as a test of faith. Others see it as a sign of end times. The Pope issued a carefully worded statement saying the Catholic Church is open to the possibility of other intelligent life in God's creation, but urged calm and prayer. Stock markets have been volatile. Not crashing, but jittery. Investors don't know how to price the uncertainty. Defence contractor stocks are up. Space technology companies are up. Pretty much everything else is flat or down slightly. The global economy is basically holding its breath. Let me tell you what's supposed to happen at the moment of alignment. The precise time when Earth, C2025 V1 and 3I/Atlas form their straightest line is calculated to be November 16th, 2025 at 14:37 UTC. That's 9:37 AM Eastern Time, 2:37 PM in London, 10:37 PM in Beijing. At that moment, thousands of instruments will be watching, listening, recording everything, every wavelength, every possible signal type, every physical parameter we can measure. If something happens, something obvious like a signal transmission or a visible change in the objects, we'll know within seconds. The automated detection systems will trigger. Data will flood into analysis centers. Within minutes, the information will spread through scientific networks. Within an hour, it'll be public knowledge. There's no keeping something like that secret. Too many independent observers. Too much redundancy in the detection systems. But what if nothing obvious happens? What if the alignment occurs and the objects just sit there, dark and quiet, doing exactly what they've been doing? That's actually the most likely scenario, and it might be the most frustrating one. Because then we're left analysing data for days or weeks, looking for subtle changes, trying to determine if something did happen that we missed or if nothing happened at all. Dr. Sarah Seeger from MIT, who's been coordinating some of the observational efforts, said in a press briefing, "We need to be prepared for ambiguity. Nature doesn't always give us clear answers. We might detect something that's technically anomalous but not definitive. We might see correlations that could be meaningful or could be coincidence. The worst outcome isn't danger, it's uncertainty. It's getting data that raises more questions than it answers." And she's right. We're probably not going to get Independence Day-style clarity here. No giant spaceship decloaking, no universal translator, no dramatic revelation. What we'll probably get is more data, more puzzles, more reasons to argue about interpretation. The scientists who think these are natural objects will find evidence supporting that. The scientists who think they're artificial will find evidence supporting that. And the rest of us will be stuck in the middle, trying to figure out what's real. But here's what I keep thinking about. Regardless of what happens or doesn't happen on November 16th, we've already crossed a threshold. We've spent months treating these objects as potentially intelligent probes. We've mobilized global scientific resources. We've had serious discussions about transmitting messages to them. We've prepared for first contact. You can't just walk that back. You can't just say, never mind, they're rocks, and expect everyone to forget. The possibility has been raised, the question has been asked, and even if November 16th comes and goes without incident, that question doesn't go away. It just gets postponed. 3I/Atlas will continue its journey out of the solar system. C2025V1 will continue its trajectory toward perihelion and then back out. Both objects will gradually fade from view as they get farther from Earth and farther from the Sun. Eventually, maybe in a few months, maybe a year, they'll be too faint to observe in detail. They'll become just two more entries in the catalogue of interstellar objects, strange and anomalous, unexplained but fading into history. Unless something happens, unless November 16th is different, unless the alignment actually matters, and then, in a few hours, we're going to find out what we've really been looking at, whether we're alone or observed, whether the universe is empty or full, whether the knock on our door is real or imagined. The countdown isn't just a timer, it's a question, and we're about to get an answer, whether we're ready for it or not. Here's the truth that nobody wants to say out loud: we've already sent our message. Not through radio telescopes or carefully crafted transmissions, not through mathematical sequences or pictures of Earth. We've sent our message through our actions, through our behaviour, through everything we've done and failed to do since these objects appeared in our sky. And if anyone out there is watching, they've already received it loud and clear. Look at what we've actually done. We detected two anomalous objects exhibiting impossible behaviour, positioned in a geometric alignment that defies probability. We had months to respond, months to organise, to cooperate, to present a unified face to whatever might be observing us. And what did we do? We argued, we hoarded data, we competed for credit. We let national security concerns override scientific cooperation. We debated endlessly while doing very little. That's the message. That's what we communicated about who we are. The meta-message. The information conveyed not by our words but by our actions is devastating. We're showing an advanced observer, if one exists, that Earth is inhabited by a technologically capable but politically immature species. We have impressive tools, telescopes that can see across light years, spacecraft orbiting other planets, communication networks spanning our globe. But we lack the wisdom to use those tools collectively. We're still trapped in tribal thinking, nation-state competition, ideological divisions that prevent coordinated action. Dr. Seth Shostak from SETI put it bluntly in a lecture he gave 3 days ago. If aliens are watching how we respond to potential contact, they're seeing a species that talks about unity but practices division. They're seeing us fail the simplest test imaginable. Can you work together when it matters? So far, the answer appears to be no. And that answer might determine whether they ever bother revealing themselves. Think about what that means. We might be disqualifying ourselves from contact not because we're too primitive technologically, but because we're too primitive socially. We haven't learned to think as a species. We still think as nations, corporations, interest groups. We're still playing zero-sum games where one group's gain is another's loss, rather than recognizing that some challenges require everyone to win or everyone loses. This connects directly to something called the Great Filter Hypothesis, one proposed solution to the Fermi paradox. The idea is that there's some obstacle, some challenge that most civilizations fail to overcome. It's why the universe seems empty despite being old and vast enough to have produced countless civilizations. Something filters them out. Something prevents them from reaching the stage where they become spacefaring, long-lived, detectable. We've always assumed the Great Filter was behind us, that we'd already passed it. Maybe it was the origin of life itself, or the evolution of multicellular organisms, or the development of intelligence. We survived those hurdles, so we must be past the danger. Right. But what if the Great Filter is ahead? What if it's exactly this, the transition from a divided planetary civilization to a unified one? The moment when a species must choose between cooperation and extinction, between transcending tribal instincts and being forever limited by them. maybe most civilizations fail here. Maybe they get to the point where they have nuclear weapons, climate-altering technology, and artificial intelligence. But they can't overcome their internal divisions quickly enough. They destroy themselves through war or environmental collapse, or they simply stagnate, trapped in endless conflicts that prevent them from achieving their potential. They never make it to the stars because they can't even cooperate on their home planet. And maybe, just maybe, the civilizations that do survive, that do pass through the filter, they're the ones watching us right now. They're waiting to see which side of the filter we fall on. Are we going to make it? Are we going to grow up as a species? Or are we going to be another cautionary tale? Another data point in the cosmic statistics of civilizations that almost made it but couldn't quite overcome their own nature. Here's what makes this moment so critical. November 16th isn't just a date on a calendar, it's a mirror. It's forcing us to see ourselves clearly, without the comfortable illusions we usually hide behind. We like to think we're special, that we're the pinnacle of evolution, that we're ready for our place in the cosmos. But look at our response to this situation. Look at how we've actually behaved when faced with potential cosmic significance. Are we really ready? The answer, painfully, is no. We're not ready. But maybe that's okay. Maybe recognizing we're not ready is the first step toward becoming ready. Maybe November 16th isn't the end of anything. It's the beginning of us finally taking seriously the idea that we're not alone, that we're being observed, that our actions matter on a scale larger than our own planet. Because here's the thing about being watched, it changes your behavior. When you know someone is paying attention, you act differently, you try harder, you rise to meet expectations. If we truly believed that advanced observers were evaluating us, would we still be playing the same petty games? Would we still be prioritizing national interests over planetary survival? Would we still be so casual about our divisions and our failures to cooperate? Maybe that's the real gift these objects have given us. Not contact, not answers, but accountability. The possibility that we're being observed, being measured, being evaluated. That possibility, even if it turns out to be wrong, even if November 16th comes and goes with no obvious revelation, that possibility has already changed us. It's already forced questions we weren't asking. It's already sparked conversations we weren't having. In the past 3 months since 3I/Atalus and C2025V1 became headline news, there's been a noticeable shift in public discourse. More people are talking about humanity as a whole rather than just their own nation or group. More people are asking what kind of species we want to be, what kind of legacy we want to leave. What we'd say if someone was really listening, that's progress. Small, tentative, fragile progress, but progress nonetheless. Dr. Jill Tarter, who spent decades searching for extraterrestrial signals, said something profound in her retirement speech. SETI isn't just about finding them, it's about finding ourselves. The search forces us to ask who we are, what we value, what message we'd want to send to the universe. Those questions change us even if we never detect a signal. They make us better just by asking them. She was right. The search itself, the possibility itself, has value independent of the outcome. We're different now than we were in August before these objects appeared. We're asking bigger questions. We're thinking on longer timescales. We're starting, just barely starting, to imagine ourselves as a cosmic civilization rather than a planetary one. But we have so much further to go. We need to move beyond imagination to action. We need to actually become the species we claim to be, united, curious, wise, peaceful. We need to prove to ourselves more than anyone that we can overcome our limitations when it matters. And here's the beautiful, terrifying truth: every single person watching this has a role to play in that. This isn't something that happens at government levels or scientific institutions. It happens in individual choices, multiplied across billions of people. Every time you choose cooperation over competition, every time you prioritize truth over comfort, every time you think beyond your immediate tribe to consider all of humanity, you're moving us forward. You're helping us pass through the filter. The universe doesn't care about our excuses. It doesn't care that coordination is hard, that changing ancient instincts is difficult, that overcoming divisions takes time. It just presents the challenge and waits to see what we do. November 16th is one moment in that larger challenge, one data point, one opportunity to demonstrate growth. So what happens next, honestly? I don't know. Maybe we detect something on November 16th that confirms these objects are artificial, and everything changes overnight. Maybe we detect nothing, and the mystery deepens. Maybe the real significance won't become apparent for years or decades as we slowly piece together what we're actually looking at. But here's what I do know: the question has been asked. The possibility has been raised. We can't unask it. We can't go back to assuming we're alone, assuming the universe doesn't care, assuming our actions don't matter beyond our own planet. The cosmic mirror has been held up, and we've seen our reflection. We can't unsee it. November 16th is coming. The alignment will happen. 3 objects will form a line in space, and thousands of instruments will watch, waiting for something to change. Maybe something will, maybe nothing will. But regardless of what those objects do or don't do, we have our own choice to make. Do we use this moment to grow? Do we let it push us toward the cooperation and unity we claim to value? Do we rise to meet the challenge of cosmic significance? Or do we slip back into our comfortable patterns, our familiar divisions, our small thinking? The universe is waiting for our answer, not a transmitted message, not a carefully crafted statement. Our actual answer, written in our actions, in our choices, in what we do right now and every day after. The visitors, if they're real, already know what we are. The question is, do we? And more importantly, Eurison, are we willing to become something better? The countdown is over. November 16th is here. And whatever happens in the sky above us, the real story is what happens down here. How we respond, how we change, how we prove to ourselves and to anyone watching that we're worth the attention. The universe knocked on our door. We're still deciding how to answer. But here's the thing about doors: keeping them closed is also an answer. Staying silent is also communication. Doing nothing is still doing something. So what's it going to be? What's your answer? Not humanity's answer, yours. Because the collective answer is made of individual choices, and yours matters. It always has. You just might not have realized it until now. November 16th isn't the end of this story. It's barely the beginning. The real question isn't what's out there. It's what's in here. What we're capable of. What we're willing to become. Ready or not, the universe is watching.